So, now take a bigger example where we have about 10 terms and we have about 12 documents. Okay. And then every element in this matrix represents our TF IDF. So, what we are going to do is we are going to be looking at this and then try to find out which document is closer to the other one. Okay. So, this is a very important exercise in the information retrieval, at least for document sets which are not very huge. So, we can actually use this if the document set is very small for you. Again, if you look at this, I keep repeating this. This one is your term vectors for document 1. That means, the document 1 contains the words T1 to T10, some of them are missing, these terms are missing. So, we have 0 values here, and then if you look at this one, term vector across the corpus. Okay. So, this is very important to understand the structure, and most of the time we will be representing our term document in this fashion. Okay. So, how do I represent them? Actually, I am not sure whether I mentioned this in the previous lecture. The TF IDF which I have spoken about could also be represented using other weighted TF IDF. One mechanism is to consider TF and then the IDF here. Okay. And then this would be replaced, not exactly the same as this, would be replaced as this. Okay. If you replace the TF with respect to 1 plus logarithm of term frequency, and if term frequency is greater than 0, and use this value, and if it is 0, it is going to be 0. So, this is again a very important representation of terms in the TF document term matrix. So, in our case we have just used a random generation of these numbers, and I represent them as TF IDF, a plain TF IDF. Okay. So, now what is required? So, we have a set of documents, we have collected the term frequencies with respect to the weighted term frequency using TF IDF or the log of those which I explained earlier. Now, I want to find out using a query how that particular query is very close to some of those documents, and then rank them accordingly. Okay. When I represent a query is going to be again a composition of terms, right. So, you can consider that as a document which is very similar to this. So, I can write a query here, and then my query can contain some values related to T1 and then some values related to T3, some value related to T7 and so on. Okay. So, this is how I construct this, and these terms, if it is found, we already have created a corpus, we already have found some frequency related value for these queries and so on, which is that what I am replacing with. When somebody gives a query, find me a document with term 1, 3 and 7. So, I go to the dictionary and then find out what are the values for these 3 terms, and then replace them, and then I construct them as a separate vector. Okay. Like these. So, I am now constructing the query, which is again very close to, is a close representation of the document. Now, it is possible for me to go and then find out how these documents are related to this query, and then probably rank them according to the highest one, which is closer to Q, would be the first, and the lowest one would be the last in that ranking order. Okay. We are going to be using some proximity score mechanism to find out how a query is related to this document. It is usually done using certain formula. Let us look at some of them. I am sure in the earlier case of binary incident matrix, query returned a set of documents for that particular set of keywords, right, but it never gave you the rank. We definitely require the rank because we want to look at the document with highest relevance first rather than something with the lowest relevance. In the case of the binary incident matrix, it is not possible for you to get that rank in that order. So, you have to assume that all documents have the same ranks, but in reality we would like to have a rank for all of those documents. So, we are going to be using some of those measures like Euclidean distance, cosine distance, cluster similarity and Jaccard similarity. Okay. I would be using cosine similarity for the sake of showing some demo and so on. So, why is it not a good idea to use D1 and D2? So, look at this. Okay. So, if you compute the distance, right, some would be long like this in the vector space. Let us assume that this is your query and then some vector would be very long and some would be very short like this. Okay. So, it is not going to really give you a good measure if the length is too long. So, it is not advisable to really go for a distance measure for finding the similarity of documents. So, which measure? As I mentioned earlier that I am going to be using cosine distance as the similarity measure because it is a normalized correlation coefficient. Why is it normalized? Because we are actually dividing the vector by the length of the vector. So, you get a unit vector there. So, it is normalized for all the vectors that you are considering. For example, D1 is normalized to the unit vector and then this also is normalized. Okay. So, for the sake of representation, I am going to be taking two words car and plane, right. So, we have a query here based on the term frequency and the length. So, we have gotten a query in this direction of length here. Okay. And then we have other documents representing car and plane in various directions. Okay. So, we have D3 here, D1 here and D2 here. D2 is very close to the plane because it may contain lot of terms related to plane than car. So, it is closely aligned to the axis plane and D3 is very closely aligned to car for the same reason. So, now when you want to find out whether Q1 is closer to D3 or D1 or D2. So, we use the cosine distance. So, what do we do here? So, we do cos of theta equal to Q1 dot D3 divided by Q1 D3. Okay. We are going to be doing the same thing for Q1 dot D2 Q1 D2. Oops. And then this is for the theta 1, let us say call it as theta 2 and then we will have another one cos theta 3 for the third one which is Q1 dot D3 Q1 norm and then D3. So, the values I am going to be finding these values. Okay. So, the rank is accorded based on how close this particular is document is to Q1. So, in this case we know visually we can find out that D3 is close. Okay. That means we can rank it accordingly. D3, if you look at the rank, D3 will come first, and then D1, and then D2, right. Right. So, this is how you find the similarity measure between documents and the query that you have just posed, and then using this you can now rank the documents accordingly, and then say okay, D3 is very close, let us take a look at the document D3 first before looking at the other ones if I do not get enough information in D3. Okay. As I mentioned earlier, cosine distance is preferred, and it is very easy to compute the score. Okay, let us look at a demo. Before the demo, I just want to mention a few things. What I am doing right now is I am posting all the demos in one space in GitHub under ROM station R, A and LP. Whatever I am showing you as a demo, those programs are available in this library. This is open sourced. You can take a look at it, you can clone it, you can make changes to that, and if you suggest some new ideas into that, or you want to add more programs to this library, you are more than welcome to do. If there are any errors found, you can also mention or send a note saying that there are some errors and you would like to correct them. I can give you access so that you can do all the changes in the code and then again submit the code back to the open source. This is something that I would like you to go and then look at it and then add value to that if you want to, or you can use this as a playground so that you can play with the demos and understand the underlying concepts in all these demos. Okay. So now let us go to the demo code. Okay. So instead of clicking and then going to the GitHub and then finally going to the collab.research.com, I have taken you directly to the space. So when you go to that GitHub space, there will be a button which will allow you to come to this collab.research.google.com. Okay, so it will open up that particular file so that you can run the application directly from this. So I am going to run this first. Okay. So what I have, I'll first show the output and then I'll probably take you to the code and explain what is going on there. Okay. So in this case, what I have done is I've used the same matrix that I had shown you. Okay, the document term matrix. This is what I am using it as an input. Okay, and then when I run this, what I get is this. Here you have a matrix containing all the documents along the x and y axis. I have taken every document in that space and then try to compute the distance from that document to that documents. Okay. So I have not used any query at this point in time, so we will come to that a little later. So if you consider document 1, it goes and then finds out the angle between D0 and D1, D2 and D10, and then it will consider D1 as the base document and then try to compute all the angles between D1 and D0, D1 and D2, D1 and D6 and so on. So in this fashion, if you look at the top side, you will have all the angles computed for all the documents. Okay. So I am going to be now considering only one document as the reference document and then try to see how closely those documents are related to that particular reference document. So, in this case I am considering D naught as my reference document here, and then I computed the ranks based on the distance. D1 is very close, D6 is the next one, and then D2 is orthogonal to D naught. That means none of the terms are close to D naught. That is why it is not showing any relevance there. So, the most relevant document for me is D1 here. So, if you go and then look at it pictorially, you will see that. Okay. So, D1 against D naught, because it is the same document, dot product of the same will result in 1, or the angle is 0 there. Okay. And then the next one which is closer to D naught is D1, it is separated by an angle 4 degrees, and then you have all the others, and then if you look at D naught and D2, it is separated by 90 degrees. Let me take you to the space where the code is available. As I had shown earlier, right. So, the D naught to D10 matrix here is computed by this. So, first I compute all the angles, and then for the plotting sake and ranking sake I am just using a reference document. Okay. So, I am just using a reference document here as 0, and then trying to find out what is the distance measure or the similarity measure in this case. Okay. Here there are some elements that you will find for plotting. So, for plotting what you require is you need to find the end distance, so that you can draw that vector. So, initial value is 0, and then the end value is calculated by the vector length, and then we plot those x and y. Okay. And then I have made the annotation, so that it is easy for you to understand that. And then at the end you have the rank order in the sorted fashion. So, once the values are computed for the reference document, you sort the document with respect to the reference document. Use case for printing the rank is the ascending order. Okay. All right. So, we have seen how these documents could be compared when the IDF TF IDF values are available. So, now let us try to construct a query and then see how the similarities are measured, and then how the ranks are computed. Okay. So, in this case what I am going to be doing is, earlier case you saw the document 0 as the reference, and then we computed the rank, and now we are going to be considering a document 2 as our query. As I mentioned earlier, right, the query can be constructed with respect to the term that are present in the queries, and it can be construed as a document as well. So, now let us consider D2 as our query. I am going to be changing my reference. We already have computed all the angles. I am only going to change the reference document as my query. I will make it as 2. Okay. And I am going to be running this program to find out how this distance varies with respect to the query D2 that I have chosen. Okay. So, if you look at the query D2, query on itself is going to give you 0, as I mentioned earlier, because it is the dot product of the same will give you the value of 0. So, you have it there, and then you have D2 at an angle D2 to D9 is 41, and then D1 and D0 are orthogonal to the document 2. Okay. So, if you look at the rank here, the query is closer to D9 and D8 and D6. If you look at the other angle, they are 61, 66, 71 and so on. That means the document D9 and D8 are closer to D2 than any other document in this space. So, in this way you can actually play with these numbers like the reference document, or you can construct a new query and then add as part of the matrix that you have here in this, and then try this. Okay. So, make sure that you use the right range. I have hard coded the ranges in this program. So, you may want to avoid that hard coding and want to give some variables there, so that you can find the actual sizes of the matrices and then do the computations accordingly. Okay. For the explanation sake, I just put together some simple program for you. So, you can go ahead and then change this in the GitHub that I have provided for you. Okay. So, this is the example of how you can construct the similarity of document. Okay, let us go back to the presentation again. So, we have just finished our cosine distance demo, and then one more thing we also want to look at when we try doing the similarity for huge document set. So, we can create one inverted index for all the documents that we have. For example, for the given to a document that I have, you can construct a term frequency and a posting. Okay. For every term, you have a column. Okay. So, this is the column for you, and then the term frequencies for the word ball across the document space. Okay. In this case, this is going to be 4. Okay. And then the postings. The postings is nothing but the documents where this particular word is present. So, if I have the word ball present in document 1, 2, 8 and 9, I just mentioned that. So, if you want to do the comparison or the similarity of the documents with respect to the query where you have the word ball is mentioned, you do not have to go through the entire document space. You can look at these postings and then say, okay, document 2 has this. So, let us go and then look at document 2 and then find out how close that document 2 with respect to this term that I have in the query. So, in the same way you can go and then look at it. So, this way you can reduce the computational time. Instead of going through the entire document set, you can only go to a small subset where that particular term is present in those documents. Okay. All right. Okay. So, this is an exercise for you. The exercise is you have to construct a TF-IDF matrix using the log weighting that I had shown earlier for the corpus Shakespeare's play. Okay. And then you need to construct a query vector containing some terms. Say for example, you pick a few terms at random in this Shakespeare's play, and then construct that as a vector, and then use the cosine similarity that I had shown in the demo, and find out how these plays are stacked with respect to the rank. So, this is one exercise for you, and the program is already available. What you have to change is you only have to change the document term matrix that I have given with the Shakespeare's play. Okay. This would be very useful if you implement this small exercise.